We experience reality, all the wonders of the world, through a multiplicity of special senses. For most of us, we mainly rely on vision. But how do we see? What structures of our bodies facilitate this experience? And how exactly does it all work? Our mystical, all-seeing journey begins with our eyeballs. Our eyeballs have 3 layers. The outermost layer is the fibrous tunic. It comprises the sclera, the whites of our eyes. It protects our eyes, at least from most unfriendlies such as bugs and dust. Maybe not a chicken skewer, but you get the point. Without the sclera, our eyeballs would be feeble. Next is the cornea, a transparent dome separated from the sclera at the limbus. It protectively shields your iris and pupil. The cornea ensures only light enters into our eyes, providing the majority of your eye's refractive power. It's in charge of bending light rays onto the lens, which in turn focuses the light onto the retina. The cornea helps make our vision sharp. Without it, our vision would be blurry. Not very fun. On to the second layer. This layer is the vascular tunic. The most noticeable component of the vascular tunic is the iris. Much like our fingerprints, our irises are unique to us. Nobody else has the same pattern as you, not even your evil twin. They are distinctly coloured muscles responsible for regulating the volume of light that enters your eye by constricting or dilating your pupil. For this to be possible, your iris consists of 2 differently oriented muscles. The outer muscle, called the radial muscle, dilates your pupil in dim light by contracting. This muscle also activates when we see someone we love or something we're afraid of. Hopefully not both at the same time. The inner muscle of your iris is called the circular muscle. This muscle constricts your pupil in bright light. Have a look at your eyes in the mirror. You might just be able to see your iris muscles working. Next are the ciliary bodies. Once again, there are 2 parts, the ciliary muscle and the ciliary process. The ciliary bodies hold the lens via zonules, spiderweb-like ligaments. The lens is responsible for focusing the incoming light onto the retina. The lens is changed in its shape by the ciliary muscles, either being flattened out when focusing on objects far away or made more round when focusing on objects close up. Without the lens, we would be totally reliant on thick, high-powered glasses to see. Such a state of lenslessness is known as aphakia. The ciliary process, on the other hand, produces a transparent fluid called aqueous humor. Aqueous humor fills the posterior chamber between your lens and iris before seeping out through your pupil and filling the anterior chamber between your iris and cornea. Aqueous humor is drained out of your eyes via the canal of Schlemm, also known as the sclerovenous sinus, if you want your eyes to have a prettier name. The final piece of the vascular tunic is the choroid. The choroid contains blood vessels to feed your eyes nutrients so that they don't starve to death. Additionally, the choroid possesses melanocytes, which produce a dark pigment that reduces the amount of light that bounces around inside your eyeballs. This helps our vision remain focused and sharp. The final layer is the nervous tunic. It is the innermost layer containing the retina. The retina lines the vitreous chamber, which contains vitreous humor, giving your eyeball its ball-like shape. The retina contains light-sensitive structures known as rods and cones, shaped like, you guessed it, rods and cones respectively. Rods maintain our vision when in dim light and provide undetailed images. Cones maintain our vision in bright light, giving detailed images as well as allowing us to see colour. Cones have special pigments that react to light, called opsins. The genes that code for red and green opsins are present on the X chromosome. Mutations to this gene lead to red-green colour perception defects, more common in males, as females possess more than one X chromosome, preventing colour blindness if one chromosome has mutated opsin genes. The opsin gene for visualising blue colour is located on chromosome number 7. There are other light-sensitive structures called intrinsically photosensitive retinal ganglion cells. Try saying that 7 times over. These cells detect light but are not used for producing images. Rather, they let your irises know when to constrict or dilate your pupil, depending on the amount of light your retina is exposed to. Upon detecting light, these rods and cones collect information about the objects we see, such as dots, edges, colours, and angles. This mysterious recognition of edges and textures allows us to recognise patterns, including human faces. Cones are highly concentrated in the fovea, located in the middle of your retina inside a fold known as the macula. Light passes through the limiting membrane, where much is absorbed by the pigmented layer. Your rods and cones hyperpolarize, reducing the release of neurotransmitter, a chemical messenger of sorts. Neurotransmitter excites or inhibits bipolar cells. Some bipolar cells love lots of neurotransmitter, known as off-center bipolar cells. Others like only a little bit, called on-center bipolar cells. These bipolar cells are modulated by horizontal and amacrine cells. These cells maximize the quality of the final output of your retinal ganglion cells. These ganglion cells are the postal service of your eye. They send the information as electrical pulses, called action potentials, along the optic nerve which exits your eye via the optic disc, your blind spot. The optic nerves meet at the optic chiasm, where some of the signals cross over to the other side. Afterwards, optic tracts relay to the lateral geniculate nuclei, 2 bulges deep in the middle of your brain. These nuclei are layered like cakes. Some layers are used for perceiving movement, brightness, and depth. Other layers are used for perceiving red and green colour waves, as well as fine details. In between these layers is where blue colour waves are perceived. Information is also sent to the superior colliculus, 2 little bumps at the top of your brainstem. They are important for visual reflexes, such as pupil constriction in bright light or tracking a moving object. Finally, the information is sent along optic radiations to the primary visual cortex, located right at the back of your brain. Here, your brain compiles all the information gathered on edges, colours and textures and forms them into a fully comprehensible image. Your eyes are fascinating and beautiful. They detect light before sending that information to be made sense of in your brain. And that is how to see.